So this problem is set up just like one from the quiz. We've got 25 newtons at 30 degrees east of north, 35 newtons at 40 degrees west of north. So we'll draw a dotted line to where north is, and then we'll use the protractor to measure 20 or 30 degrees east of north. And then it's 25 newtons, so a line will be drawn that's 2.5 centimeters long with an arrowhead on the end. And then we'll measure to the west same thing with the protractor. We'll count over 40 degrees, put a dot, then we'll align the ruler, and this time it's 35 newtons, so we'll go 3.5 centimeters, put an arrowhead there. So that's what it would look like if we were just looking at the box that's being pulled. But now in order to get what we have here, we need to move tip to tail. So we'll take this arrow and we're going to draw that same north facing line so we have a reference point, and we're going to move that arrow over there, that vector. And so from that dotted line we'll draw the vector, measure over 30 degrees, and then draw it as 22.5 newtons long. And all we've done is move that, so now it's drawn from the tip of the first vector to the tail of the last one, or the next one, and then you'll draw from the beginning to the very end for your net force here. And when you measure that out, it ends up being right at 5 centimeters, and so that is equal to 50 newtons for what you have. And then you'll measure that angle there. You can see the angle comes right over to the side. It's right at about 17 degrees, and because it's toward the west from the north, we say 17 degrees west of north. For the calculating part here, we can sketch again what's going on. This part doesn't need to be to scale, but something close is really helpful. Again, 30 degrees to the east for 25 newtons, and then 40 degrees to the west for 30 newtons. And we're going to break it into the x and the y. And so the pink one is the y, and the orange one is the x, and that'll be for both of them on there. And we'll need to be able to use the angles in order to break this up into what we have. So what we can do for x1 is it'll take the 35 newtons times the sine of 40, and then for x2 we take the 25 newtons times the sine of 30. And the reason we're using sine for the x's is because those x vectors are opposite where the angles are, and then in the y's it ends up being adjacent to the angles. So sine and cosine are not hard and fast to x or y, but it is always determined by the way that the triangle is set up. So in the x direction we've got 22 newtons heading toward the west, and then we've got 12.5 newtons heading toward the east. And in the y direction both are pointing north, so we're adding up the y directions, so we get 49 newtons. And then in the x direction one of them is negative, so we have to identify that as such. And it doesn't matter which one, but it just helps us determine the direction that we're going. So we've got a magnitude of 9.5 newtons, and because negative is assigned toward the west, we'll keep it to the west in this case as well. So we have 9.5 newtons to the west, and we have 49 newtons to the north. And now we can set up our new triangle in this situation. So our resultant vector, our total force, is what's in the black line there. And we can determine what that is by using Pythagorean theorem. A squared plus b squared equals c squared. And so we'll do 9.5 squared plus 49 squared. We'll get an answer there, and then take the square root of it in order to get the net force here of 50 newtons. And when we solve for our theta, our calculations should be decently close. It's not always going to be perfect, but we take the opposite over the adjacent. It gives us tangent of theta, so theta is the inverse tangent of 9.5 over 49. That gives us an 11 degrees, which is pretty close to what we have above at our 17, a little bit farther off. The stuff that's up on top is the measured, and then the calculated is what we have on the bottom.